Do you ever look up at the night sky and wonder what lies beyond the stars? It's natural to be curious about the universe, and there are many myths out there about it. Many of us have accepted these myths as fact, but they may not be as true as we think. In this video, we'll explore 5 of the most common myths about our universe and what the reality is behind them. Watch this video till the end to learn more and expand your knowledge of the universe. Number 5. If the universe is 13.8 billion years old, then we shouldn't be able to see objects 46 billion light years away. After all, nothing can move faster than the speed of light. The light from the sun is 8 minutes and 20 seconds old because it takes light 8 minutes and 20 seconds to traverse the distance from the sun to the Earth. But there are 2 important points to realize there. One is that the sun and the Earth aren't moving away from or towards each other during the light's journey, and the other is that the space between the sun and the Earth isn't expanding. On the largest cosmic scales, the universe has both of these factors in play. Imagine a galaxy that was 10 billion light-years away from where we are now 10 billion years ago. Imagine that it emitted light. If the fabric of the universe weren't expanding, it would take 10 billion years to reach us. But if the galaxy were moving away from us, limited by the speed of light, it could be as far as 20 billion light-years from us by the time the light gets there. And if the universe were expanding, it could be even farther. If our universe were made out of mostly radiation, we could see up to 27.6 billion light-years away in a 13.8 billion-year-old universe. Number 4. Nobody knows how gravity really fundamentally works. The forces affecting our universe, gravitation, governed by Einstein's general relativity, and the electromagnetic weak and strong forces, described by quantum field theory, are easy to observe and measure. The theories underlying them are separate, with general relativity describing the relationship between matter and energy to the curvature of space and time, and quantum field theory describing the interactions between particles occurring in that space-time. You might worry that gravity must inherently be a quantum force in nature, and that there should be gravitations mediating that interaction. You might also worry that we cannot calculate how the gravitational force or field ought to work in quantum situations, like for an electron passing through a double slit and interfering with itself. But the purpose of science is to explain observations, and general relativity does so for absolutely all of them. Not just sufficiently, but perfectly, to the very limits of what we're capable of observing. Every theory has a limit to its range of validity. General relativity will break down at some point, like at the singularities inside of black holes. Number 3. The Big Bang was the birth of space and time. The universe has been expanding and cooling for billions of years. Everything was hotter and denser in the past. And if we extrapolate back arbitrarily far, we'd arrive at a point of infinite density. Theoretically, this was realized as early as the 1920s by cosmologists like Alexander Friedmann and Georges Lemaitre, with the latter calling this state the primeval atom from which everything emerged. When the leftover radiation glow predicted by this picture shifted into the microwave portion of the spectrum by the universe's expansion was detected in the 1960s, the Big Bang was confirmed. Extrapolate back arbitrarily far, and you arrive at a singularity, where space and time as we know them emerged from. Only that picture isn't right. If the universe's temperature, and hence its energies, ever rose above a certain point early on, the fluctuations in the cosmic microwave background would be larger than what we observe. The fact that they are only a few parts in 100,000, first measured in the early 1990s by COBE, tells us that there must have been a state before the hot Big Bang that our hot, dense matter and radiation-filled universe emerged from. There was a prediction made as to what that state would be in the 1980s, cosmic inflation, which set up and gave rise to the Big Bang. Number 2. Space, time, and gravity could all just be illusions. Maybe they're not fundamental. Maybe they're not really real in some sense. There has been a lot of buzz about a recent idea that some of these properties may emerge from something more fundamental. Sound waves emerge from molecular interactions, atoms emerge from quarks, gluons, and electrons, And strong and electromagnetic interactions, planetary systems, emerge from gravitation and general relativity. But in the idea of entropic gravity, as well as some other scenarios like qubits, gravitation or even space and time themselves might emerge from other entities in a similar fashion. But at the root of this is the fact that there are close relationships in the equations that govern gravitation and those that govern thermodynamics. Normally, we take the point of view that gravity and particles are fundamental entities, and that thermodynamics is emergent, describing the aggregate properties of a large number of more fundamental things. In fact, the laws of thermodynamics do emerge from a different, more fundamental field: statistical mechanics. Gravity may yet emerge from something more fundamental: strings, loops, hairy black holes, Planck particles, or some other theoretical construct. The key, however, is that the predictions of this more fundamental idea must differ from what general relativity predicts, and that hasn't been put forth in any verified manner. Number 1. It's all just a theory anyway. The Big Bang, just a theory. Gravity, only a theory. Even the entire field of putting these ideas together is called theoretical physics. It's not like these are facts, truths, or even laws. They're only theories. But that completely misses the point of what a scientific theory is. Facts are the most basic elements of science. You make an observation, and that's a fact. You make a measurement, and that's a fact. A single experimental data point is a fact, and so we collect as many of them as we can, and devise setups to collect even more. When you notice that things are correlated, that relationships between various measurables, observables, obey a particular form or equation, that's a law. It's only when you can put together an overreaching framework that not only explains the facts and encompasses the laws, but also makes new predictions about things you can go out and observe that you've got a scientific theory. If you then go out, validate and verify your theories and push them to the absolute limits, that you've got a theory as good as the Big Bang or general relativity. Which one is the more interesting part? You can share your thought in the comments section. If you enjoyed the video, so like, share, and subscribe to my channel so we can come back with more interesting content. Thanks for watching.